Fitzhugh network model source. So it's decomposed on 4 parts. First part will present neural networks, some definition, history, applications, and second part is about the dynamical system with delays. Third part it's about the hop-eld neural networks, and for the fourth part is about numerical simulations, and finally we will close with conclusion and outlooks. So, for about the neural network, it started.
ولا يهمك مرة ترى تصير متكررة.
اوكي.
المشكلة عندنا تقنية.
ننزل على الكلير اوكي ولا؟
لا حتروح لحالها.
اوكي. About 180-90, the first learning law of neural networks has been proposed by the American psychologist Dr. James, known by the name of Hibb's law. After that, in 1943, Coolidge and Pitts made the first model of biological neuron. In 1987, Rosenblatt made the great work, and he constructed the first neural computer with application on facial recognition. And in 1982, hop-eld discovered the recurrent neural network. About applications, we have image processing, finance, home appliance, simulation, and machine learning, deep learning, and artificial intelligence. And after that, we have some definitions. First definitions it made by Dr. Robert H. Nelson. What's an artificial neural network? It's a computing system decomposed by some connected elements, dealing with information given by the dynamical states of external data. This is your definition. For the mathematical definition, what's a neural network? It's a formal neuron is nonlinear function whose value depend on some parameters called weights. And here we have a biological neuron versus artificial neuron. Here we have the nucleus axon and the terminal axon. The same thing here in artificial neuron. We have some information given here, x1, x2, x1, x2, x0, and the W here are the weights, call it the weights. And the cell body, it compute this information with function called the activation function. And we have here the output f of sum of W x e plus b. Now we start with the dynamical system with delay. And we have this system x point equal f xt xt minus tau. Tau here it's called the delay. T, the variable, and tau is called the delay. I will give some results quickly. So we suppose that f is continuously differentiable such that f0 is equal to 0. And 0 here is the equilibrium point of our system. The linearization of the system 1 is at the equilibrium point is x point is equal to L point x, where L is continuous linear function. And here we use the Reese's representation theorem, which prove that there is L phi is equal to this integral. So now we'll decompose C with the formal adjoint equation, and we will have this operator T from Cn2 to Cn2. So the work here is to decompose our parameter, our application, to two bases, P and P star. So we have this lemma T is continuously completely continuously with T is an operator, and we have the infinitesimal generator of the family of transformation T. It's A phi eta. The domain of A is dense in CMT, and its derivative with respect to T, it's equal to T eta. We have here some definitions. The resultant, the B, it's a linear operator taking Banach space into itself, and the resultant set rho B is the set of values lambda in complex plane for which the operator lambda I is the identity lambda I minus B as a bounded inverse in dense and dense in B.
Operator B itself is bounded or not?
Bounded, yes.
Is written on a linear operator.
The complement, what?
B is also bounded, yes?
Bounded, yes.
Okay.
The complement of the complex plane is called the spectrum of B, and it's denoted by sigma B. The spectrum of sigma B is divided on three types of points: the residual spectrum, continuous spectrum, and the point spectrum. We'll finish with definition. The null space MB is the set of all phi MB for which B phi is equals 0. For a given lambda sigma B, the generalized eigenspace of lambda will be denoted by M lambda B. So here we have the characteristic equation. So here we have the characteristic equation. It's equal to 0. So we have delta lambda is equal lambda I minus this integral. The roots of this integral have real parts bounded. And we have here some theorem. Quickly I will go to the second part, which is the bifurcation. What's a bifurcation? Bifurcation deals with the dependent equation on some parameters lambda. In particular, it's study the critical value of lambda, where the critical change occurs on the structure of the set of solution. Such a change is called bifurcation. The point lambda is called the bifurcation point. We consider here this differential equation. X1 is equal r minus x squared. R here is the parameter. And if we change the r, if r is negative, r equals 0, and r positive, here the different point of equilibrium. If r negative, there is no point of equilibrium. If r equals 0, we have only one equilibrium, and if r positive, we have 2 equilibrium points. And here this diagram is called the bifurcation diagram. This part of negative real parts we have unstable and stable system.
What is the negative?
The negative, not exactly. The R, not exactly negative real parts.
Here you are representing not with you are representing R with respect to E. So this is another.
Yes.
Okay, that's fine.
Negative real parts for characteristic equations. And here we have hop-eld real neural networks. So definition of hop-eld neural networks is neural network with, where all the neurons are connected with two channels of transformation. Like this model. Here we have three neurons, X1, X2, and X3, and we have two layers. This is the first layer, and this is the first layer, and this is the second layer. So, between layers, we have delay transmission. There is delay transmission. We have two channels. First delay is 1, and the second is 2, between X1 and X2, X1 and X3. In the same layer, we have no delay transmission between X2 and X3. This model is given by this dynamical system with delay x.1, x.2, and x.3, and we have here the delay between x1 and x2. This is the activation function, and x2, x1, and x3, x1. Where xi are the states of neurons, to the synaptic delay between the two layers, mu I, internal attenuation rate of neurons in the first and second layer, CIG are the coupled weights, and FI coded activation functions. So now we suppose that tau is equal to 1 plus 2. And mu1 is equal to x t minus 1, u2 it's x2, and u3 it's x3. The initial system is equivalent to this second system if we change x by u, and if we linearize in the neighborhood of the equilibrium point this system, we find this.
What is the equilibrium point?
0.
Is it unique?
0, yes. 3, 0.
It's 0. What is unique? You have another one? Or you have just that?
And this
0?
system it's unique.
Cannot be. Impossible. Because look, you have F1, F2, F3, and all of that type. They are non-linear functions. If you look at it, just.
Okay.
I am helping you. Just.
Okay.
Just look. What is the definition of the equilibrium?
If the
derivative is equal to 0. If the derivative of x1, x2, x3 is equal to 0.
Yes.
That means the right hand side it will be equal to 0.
Equal to 0.
You have near function in the right hand side.
No.
F1, F2, F3
Are
are what? Can be anything. Can be 1 over something. No.
no.
Take it linear.
Keep discussion later.
Linear, yes, but there is
Mustafa.
many difference. Maybe it will be a hyperbolic tangent also.
Huh?
A hyperbolic tangent,
Huh? What?
sigmoid, or a hyperbolic tangent.
Yeah, sigmoid is what? Is non-linear.
We discuss later
Yes,
after
this is
finishing.
FI.
Okay, that's
The
fine.
I are like this. This definition like this.
Okay, that's fine.
It-
Yeah, that's fine.
It's not linear.
Okay, that's fine.
So, Ki is here. Ki is the derivative of I at the point 0, and we have this assumption mu2 point mu3 is equal to C3 C23 square K2 K3. So now the characteristic equation of the above system is given like this, by two parameters lambda and tau. And you have this equation. This characteristic equation or the roots of these characteristic equations depend on tau. And we simplify here by the notation. We make A, B, C, and D are these parameters. And we consider this following assumption: A mu1 plus B mu2 plus C mu3 plus D is equal to mu1 product mu2 product mu 3. So under this assumption, we have lambda equals 0, its root. If we have C20 is parameter, this parameter C21 and C23 giving here in this system. Here we have C21 and C21, C31 here, this weights. So these parameters in this case are the bifurcation parameters. So first lemma, if C21 is different from C210 and C31 is different from C310, lambda is equal 0 is 0 is a simple root or single root of the characteristic equation. If we have equality, so the 0 is double root of the characteristic equation. Second lemma, all the non-zero roots of the characteristic equation have negative real parts if and only if C21 is equal C201 and C31 is equal 310 and 2 between 0 and 0 is critical value of this 0. First theorem. If the condition 25 is satisfied, so Bogdanov takes bifurcation undergoes in our system. And using now normalization of time by t is equal t divided by 2. We will write C21, C31 as the new expressions. C21 is equal C210 plus alpha 1 and C310 plus alpha 2. Alpha 1 and alpha 2 are very little value of real value. And now we will apply some developments in the neighborhood of C21 and C31. We have U1 dot, U2 dot, and U3 dot. Some developments are made here. Mu1 U1, C20 plus alpha 1, K1 U T minus 1, because we normalized the time by 2. So here we have T minus 1. The same thing here for T2, U2 and U3. So our system now it can be written as a function differential equation. U.1 is equal LU U2 UT plus F U T U, where U it's vector composed by U1 U2 U3 and LU phi. It's an integral here defined like this. Theta, it's this expression is defined by this expression A plus B. A is matrix and B is matrix. It contains only the bifurcation parameter C210 and C310. Now we define bilinear form, which given in the second part. C phi is given by C0 phi 0 minus integral, and we have the basis P and P star, which decompose the eigenspace of our our operator. So we have P and P star defined like this. P vector phi, it composed by P1, P2, and C here it's a column composed by C1, C2. Phi it's between -1, 0, S between 0 and 1, and we have here some equalities, and we have A plus B, P1 0 equals 0, A plus B, P2 0 is equal identity plus B, P1 0, C2 0, A plus B is equal 0, C1 0, A plus B, it's equal C2 0, identity plus B, and square product Ci phi G, it's equal delta E IG. The explicit forms of phi after calculations and psi, it equal this, we have here phi, this matrix, and CS, it's this matrix, this is P1, P2, and this first column is P1, second column is P2 with these given parameters. Now we will start the normal form. We consider this system. So C point and X point is given by these equations. Definition: system 51 is called bifurcation normal form. If all generic system of 32 with equilibrium point X equals 0 satisfies the same conditions of bifurcation at the point alpha equal 0. This is the parameter alpha. So it's topologically equivalent at the neighborhood of 0 for some values of sigma I. We have here our first proposition. The associated normal form of the system 26 is given by Z1 point and Z2 point, where eta 1, eta 2, eta 3, eta 4 are given and depends of the parameters of our system K, alpha, gamma, C12, C13, C23, C310, C210 also. So under assumption 25, the assumption, just I remember, this is the assumption 25. Under assumption 25, if the second derivative of Fi at point at 0 is different from 0, so the center manifold system 26 is equivalent to system 33, and the truncated normal form of system 33 is given by this system. So here in this equilibrium form, we have two equilibrium points, E1 trivial equilibrium point, and this is a non-trivial equilibrium point. Our last theorem here, for sufficient alpha 1, alpha 2, the system 34, the previous system, undergoes cross-critical bifurcation on the line T, eta 1, eta 2, where eta 1 is equal 0, eta 2 in its real. At the trivial point E1, 0, 0, for system 34 undergoes an unstable up bifurcation in the half line H1, eta 1, eta 2, where eta 1, eta 2 is equal 0 and eta 1 is negative. At the non-trivial equilibrium point E2, system 34 undergoes a stable up bifurcation in the half line eta 1, eta 2, where eta 2 is equal eta 4 divided by eta 3 multiplied by eta 1, and eta 1 is is positive. Here we have the bifurcation diagram of for the three cases. This is the most critical bifurcation, T. This is the half line H1 and the half line H2. Some numerical simulations. So we let here mu1, mu2 equals 0, 0.2, mu3 equals 0.5, and C12 equal 2, C13 1, and which equal C23, T1 equal T2, it's equal 2 also. So using this lemma, previous lemma, C210, the critical value of C210 is equal minus 1, and the critical value of C31 is equal 1.3. So for two larger than T1 plus T2, it's equal 4.3, because here we have T1 and T2, it's equal 4, the sum. And we suppose that F1 is equal equivalent tangent plus 0.1 cosine x. F2 are equal to F3 equivalent tangent to x of x. So here with some modification of alpha 1 and alpha 2, the parameters of C210 and C310, we will find this waveform of X3, and the phase diagram for the three variables X1, X2, X3, and we have here the torus critical bifurcation for system, because the eta 1 is equal 0, eta 2 in this case is minus 0.0, eta 3 eta 4 1.0. So we are in the first condition, and we have torus critical bifurcation. We'll change now the parameters alpha 1 and alpha 2, and we'll find the second part of the theorem, and we have eta 1 equal minus 0.0, near the 0, eta 2 equal 0, eta 3, and eta 4 minus 0.9, and this is the wave diagram of variable x1. Phase diagram of variable x1, x2, x3, and we have the limit cycle at the origin generated by the hop bifurcation on the half line h1. The bifurcation of hop generated at the half line h2 is given by this phase diagram, and we change it of alpha 1, alpha 2. Alpha 1 is equal minus 0.6, and alpha 2 0.5. This is the package of MATLAB used. We used the Simulink for these simulations. And these are some waveform and phase diagram of x1, x2, and x3. So now this is the Fitzhugh nagumo model. So here we have 4 equations, and we choose the parameter C1 and C2. So the problem here that in the characteristic equation, in the first part, or within the previous part, we used the C21 and C31, and we find it like this. Let's remember. So what we have here, C21 and C31 are not dependent. There is no product between C21 and C31. But the problem in Fitzhugh nagumo model now, that the characteristic equation you have product between C1 and C2. We're trying to find a solution for this problem. Until now, we didn't find a solution, but we are working on now. So that's it. And thank you for your attention.
Thank you very much. There are any questions, please?
I have a question. Doctor?
Yes.
Please show me condition 25.
Condition 25, okay. This is the condition 25.
Probably you can give concrete example, but I'd like to understand. We have two functions
Yes.
from three variables, mu1, mu2, mu3, okay? And another function depends only from product. We have two functions. For any D, there is intersection point of these two graphs.
This is just the weak state.
Every time it has solution, this
Which function is
if
that?
you look as equation.
Hmm?
Equation 25.
25. It's okay. You don't talk about that.
25.
No, okay.
25.
Right?
And this equation, if you look mu1, mu2, mu3 as parameters.
Mm. Yes.
This equation has solution.
Yes.
Can you explain to give concrete examples? And I like to understand, not my question, not.
Complete example of this equation.
Please explain that these two graphs every time for any D intersects in some.
Or it has a solution.
Has this
Explain.
solution? Yes.
It has a solution because what we did is we changed some variables and we find and we try to do it, but to deal with it, and we find that we find a unique solution. There is what we find, but I worked on some article dealing with this type of equation, and we find with some changement of variables, we find the solution.
Maybe his question is set. The left-hand side is a plane
Yes.
in R3, and the right-hand side is a function x, y, z. So you have two surfaces. Those surfaces can intersect or not. This is what.
Even if one of them is parabolic, has one linear function, not always they have.
Maybe it's for some. It's for in the
For
some
some,
condition,
yes, for
or
some,
maybe
yeah.
A, B, C, D.
For some, yeah,
Yeah,
until
or
by asking, is this equation solution or not?
Yes, for some condition you can find it.
Not always.
But we suppose it here we put this hypothesis to be in exactly to find C210 and C310 like this expression. That
Okay, it's a little bit strong.
yes, yes.
Not very
Yes,
easy.
I know it's strong.
Okay, sure.
One question, please. Another question.